Hello everyone, December the 9th. Um, so we still haven't done this yet. It's been a while. But I mean, the solution is here, which is good. And last night, actually, after we finished, I played around with the idea of doing prefix sum because I think it is prefix sum. I mean, in the comments, somebody talk about prefix sum. Yeah, here, I prefix sum. So I was trying, but it was not very successful earlier. You see that? I got it wrong. So I'm going to have to play around with it again and see if we can make this a little bit better. I do believe this is the way to go, but I need to. I mean, when I was doing this yesterday, I didn't really write out everything, like to check everything. I did not. So today I'm going to do that. So that's that. And went into today's challenge, whatever it is, just going to get it done. Tomorrow, I have lots of lemons. No, I got it's a gift. I have I think about 15 lemons, 16. I don't know how many, tons of lemons. So when life gives you lemons, what do you do? I'm gonna make some lemonade tomorrow, but I don't have a squeezer, so I'm ordering one from Walmart. But they're telling me that it might not be available, so I'm actually at a loss. What if I can't have a squeezer? What you gonna do? How are we gonna get lemon juice? I mean, I have a blender. I probably need to check online. Like, what do you do if you don't have a squeezer and you want to have lemon juice? We'll see, but it'll be fun. I never made lemonade before. All right, let's see what this one is. Maximum product of split binary tree. Given the root of a binary tree, split it into two subtrees by removing one edge, such that the product of the sums of the subtree is maximized. Return the maximum product of the sums of the two subtrees. Ooh. You need to maximize the answer before taking the mod. Okay, so damn. I mean, depending, we can actually check every single edge, right? Yeah, so every single edge, if we break it, when you break an edge, what you get is a subtree. So if I have a subtree sum, right? And then for the remaining is the subtree sum of this minus this. Now I have this. Now we just multiply the two. So the first thing we do is to find the subtree sum of all the nodes, right? How do we find it? I think what I'm gonna do is, you know, is simply add. I can change the value. I mean, I'm gonna change it. You can't stop me. I'm gonna change it. Like this, instead of 2, this will be a new value. Yeah, this actually gonna make things easier to calculate everything. So we get the sum of everything, and then we're gonna loop through again. So it's gonna be 2 pass. I'm afraid 1 pass might not work. Actually, yes, 2 pass. We do need 2 pass because I want to try every single node, right? Because every single node we can have a cut. Every node can have a cut. So we get the sum, and then we're gonna go through every node except for the first node because there's no cut. So I'm gonna go this. We'll say, okay, I'm gonna cut this. I'm gonna cut this, and this value is the same. And I'm gonna cut this, right? And then we just yeah, that's about it. Not too bad, not too shabby. Okay, let's get this done. Oh, I borrowed a book today. I put a book on hold today. I'm gonna have to see if it's still available. If they have done it, it's not available. I put it on hold. I don't know. They didn't send me an email today. All right, so we're gonna say def prep sum node, don't return anything. If, well, we do have to return, right? Actually, we don't have to return. No, we don't have to return. I'll change the thing itself. So what we do is, if node, right, we're gonna say perhaps some node dot left, perhaps some node dot right, okay, and node dot val equals plus equal to node dot left dot val, node dot left and dot right. Oof. If node dot left, that would be easier. What would be easy to do? If node dot left, can do this and plus equal to if node dot left else 0 plus node dot right dot val if node dot right else 0. Okay, so this one is a prep sum root. Then we're gonna find self dot rest equals 0 for the maximum, and dfs also none. Okay, so what we're gonna do is I want to break myself, right? Break myself. Then we can have the total shall equal to root dot val. That's a total. I don't have that. I can just say root dot val. Yeah. So if I break myself, basically I say self dot rest shall equal to maximum self dot rest node dot val if node, right, node dot val multiplied by root dot val minus node dot val. Right, so we've done that. We say dfs node dot left, dfs node dot right, and then we call, yeah, we can actually put them together, put in here. Right, I do this, and then dfs root, then return self dot rest. Yeah, I shall work. Yep. Oh man. Don't know, man. It's not the first time I'm making this type of mistake. Forgot a mod. Okay. I guess I have a similar solution in the past. Oh, I take it out. Huh. That works. It works. Man. always forgot this. It's not the first time. Would not be good in the competition, you know. Find the sum of each subtree. All right, so back on this one. I still have the things from yesterday, so we can analyze why this one doesn't work. So we know it's going to be a sum. So if I make shall be 0, so with 1 division 0 0 0 1 1 2 3 4 5 5 6, right? Then partition number 2, you start from partition number 2, yeah, we start from this, and this will check, that should be a 0, right? And then we check this will check this as well, as it's based on the primes. Ooh, wait, hold on, that's not a 1, that's a 0. Wait, hold on. We have to redo this. All right, we have to redo this. Hold on, I'm gonna turn off this. We'll go back to solution 2. Okay. Go back to solution 2 and let's print it out. Yeah, I just want to see how it goes. So we're gonna print out dp at each turn. Okay. Print out dp at each turn. So the dp, that's the first, that's the second. What about a third? Oh, no, that's solution 3, solution 2. Wait, hold up. dp and then dp. Yeah, we need another dp at the end. There we go. So this is what we have. So with 1, we have hold on, 2 3 5 4 2 1 8 5 1 3 1. Okay, and then with 1 we have 0 0 0 1 0 1 1 0 1 0 1. With 2, because I start with this one, right? So we need to find a previous. Yeah, because I am 1, and then we say can do 2. That's a 0, so it'll be 0 0 0 0. This is 0. This we check. That's a 1. Yes. This we check this. That's a 1. Not because that's the previous prime. This is 0. This 1, check this. So we have a 1. And because how many? So we check for the previous one. So that's a 2. 3 is a 0. This is, I have a 1. I have a 2. I have a 3. Right? So 1 1 0 2 0 3. Yes. 3. So for 3, partition 3, so I have 6. So this is the first one. So it would be all 0 to start with. So here in the partition 2, that's a 0, right? And this, we need partition 2, that's a 0, because we don't have partition 2. This would be 0. This, partition 2, I have a 1. This would be 0. This, partition 2, so we go here, we have a 2, and so that's a 3. Yep, okay, so analysis is correct. Now we just need to see how can this one be done in a faster version. Okay. Because for the partition 2, we're just looking for the prime. So what we're saying is I'm going to do a prefix sum based on the what we have previous. So if what we have previous, the pre-sum is going to be 0, 0, 0, 1, 1, 2, 3, 3, 4, 4, 5. Right? So when that happens, we have 1, 2, 3, 4. This one we're going to take, that's going to be 0, right? And this is a 2, so that's going to be 0. And this, the next one, no, actually, let's write it. 2, 3, 5, 4, 2, 1, 8, 5, 3, 1. So, hold on, I got it wrong. 4, the previous, this pointed to 0, so that's a 0. 2 is going to be 0. 1, okay, 1, so we need to find a previous prime. So we look back, we find a previous prime, right? And we can actually use this prime. It's a prime, so we use the prime, so it's going to be 1. And 8, we find a previous prime, so that should be a 1. And 5, we find the previous prime, and 5 is a 0. 1, we find the previous prime. That gives us, that gives us 3. That is not right. Because we go for 8. It has to be prime. ¿Sabe? It has to be prime. So this prefix sum is not right. Okay? This prefix sum is not right. It has to be a value. We only add value if it's right before a prime. So prime itself is going to be 0. We're not going to add anything. So 0, 0, 0. And this one, right? This one. And for each value, we need to look to the next one, right? Well, this value is not a prime. The next one is a prime, so this one needs to be add. That's a 1. As a prime, we just add. And this, we have a value. We'll look at the next one is not a prime, so we don't add. And this next one is a prime, so we add. Prime don't add. This we add, so that's a 3. This has to be a 3. And the last one we don't add because it doesn't have the next one. Yeah, because we looked for the previous. So that should be the one. So now the 5 0 is this one. We need to look just to the most recent prime because everything will be added together. So we look at the most previous. So that will be a 2. That's a 0. One will be a 3. Right? So we just need to look back to the most recent prime. Actually, we don't even need to look to the most recent prime. We just need to look for the previous value. Because we're going to go back, right? We're going to go back to a prime. Now, let me think. We just need to go more than the minimum length. Wait, hold on. Do we just need to go on a more minimum length? Let me think. We just need to find the most recent prime. That everything, right, prime and everything else is not gonna be prime. So we just go, find the most recent prime, and that value shall suffice. And then I'm going to produce a prefix sum for this. So we add this. This is follow. And this shouldn't add. This will add. It just add by itself. Now prime look. This is a 2. So we add to it. It'll be a 3. That will be a 3. That will be a 3. So the last one, we start from here. Look for the most recent prime. That's a 0, so that'll be a 0. Right? 8, I'll look for most recent prime. It's a 0, so it's a 0. 5 is a 0. 1, look for the most recent prime. It's a 5, so that's a bit 1. 3 would be 1. 0 is 0. And 1, look for the most recent prime. That should be 3. Okay. Most recent prime. Can we just go back once? Yeah, why can't you just go back once? Because the only value change is that the prime, right? We only add a value to the non-prime if it's followed by a prime, and we have multiple. Yeah, so if they are all non-primes, we never add them, and I myself is a non-prime. So if the previous is a non-prime, we're not gonna add. Got it. So yes, this is a little bit wrong. So we are going to fix this. How are we gonna fix it? So we produce this and we have a prefix sum, right? So we're gonna just go through everything. That's what we're gonna say. We actually gonna go to not go to the last one because the last one is, it's irrelevant, right? So we're just minus 1. And what we do is every single one we say if I am not a prime, right? If this is not a prime and sj plus 1 is a prime, if I'm not a prime, the next one is a prime, then we'll append this and dpj, right? So if I am not a prime, the next one is a prime, so we're gonna add this. Else, any else situation, we just add the same thing. So, okay, that's that. Now, we have the temp, we have the presum temp, which we can actually do exactly the same thing as what we did earlier, but it doesn't really matter actually. It doesn't matter. So we're gonna go, this is what we'll go. So we say if in prime, let's handle it slightly differently. If I'm not a prime, right? If I am not a prime, you still have to go to minimum length, right? We still have to go the minimum length to check that value. Yeah, which means if there's any prime in between, you shouldn't count them. Yeah. So what I think is we start from minimum length times I minus 1. Start from that. And if it's a prime, we simply just ignore it. And presum j equals presum j minus 1 plus temp it might be easier that you just handle the presum separately. That's just my thought process at the moment, right? Well, just we do the temp, okay? We do the temp thing first. So we have the temp, and I have this. If we just say if j is not in prime, right? Then we just simply say temp j shall equal to pre-sum j minus length plus 1. So that's j minus length plus 1. So from j minus length plus 1 to j, is minimum length. So we are actually looking at the pre-sum at the value, right? Which should be the same. Yes, which should be the same as that. This one should be right. So temp j shall equal to this. And then blah, 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 we have the temp, right? We have the temp. Then we're going to produce a pre-temp, pre-sum temp. So it'll be the same thing, right? We just copy and paste this. Pre-sum temp. For j, and then we say if j is not blah and blah. And then, yeah, it's called pre-temp. Let's call it pre-temp. Okay, pre-temp. And if j, blah and blah, and then we say pre-temp. This is going to be temp. Right, and then we do this. Okay, let's see, solution 3. Now solution 3 passes. Now, I mean, we can combine the two. That's fine. It's the same thing. I mean, honestly, we can start from this. So we don't have to start from 1. Ooh. Times I? Yeah, I don't know. Still have to. What happened? Wait, hold on. I didn't do anything. What? Oh, the length is not right. Yeah. Too easy to get it wrong. Yeah, the kind of, you just want to maybe do it inside here, right? Oh. It's not in prime. We actually do. We say if sj plus 1 is in primes, right? Then we can say, if we do it here, we say pretemp equals 0 times n. And we say if this is not in prime, but the next one is in prime. So whatever I have, I need to add to it, which means pretemp j, right, shall plus equal to pretemp j minus 1 and plus temp j. Else pretemp j shall just plus equal to pretemp j minus 1. Which means this shall happen, and only this will add this. So we don't need any of this. Oopsie doozy. String index out of range. Because you go to the end. Now, j is j plus 1 smaller than n, and ooh. Oh, I already added, so I just need to add this. There we go. So this is to create a prefix sum. I would say create a prefix sum where we only add value if si is points to a non-prime and si plus 1 points to a prime. This way, presum t is the sum of all possible is the sum, right? Is the sum of previous partitions, right? All possible previous partitions, right? All possible previous partitions ending, right? Ending at some index before t. Right, so we create this, but as we do this, we can do, okay, so now the question is, does this work? But apparently it does not. Okay, so we still need to fix. It's not correct. Okay, it's fine. We need to analyze this again. Why does this wouldn't work? It's a minimum length is 3. Result 3. Answer is 1. Something is seriously wrong. Okay, no worry. We go back to basics. Minimum length is 3. Okay, so let's go back to solution 2 and print out all the DPs so we can have an understanding. Damn. It's bad, right? It's bad. I think I can print out DP here. No, it's the same thing. I still print out DP at the top. And I'll print out DP at the end. Okay, so it's the same thing, but apparently it's slightly different. I have 0. Wait, hold on, I need a 0, 0, 0, 1, 0. Now the first one is the same. 1, 0, 1, 0, 2. So 1. But we do have this? Huh. Oh, this one doesn't count. So that's why it's 1. Yeah. So we do the same, right? 0, 0, 0. This will be 1, 1, 1, 2, 2, 3, 3, 3. Okay, so minimum is 3. So we do this. We start from 1, 2, 3, 4, 5, 6. Start from this. And this is good. So we look for the previous. No, we have to go 1, 2. We have to go to this one. So you're saying we need to find, because this one is are you saying this has to be j minus length 1, 2, 3, not plus 1, j minus length. Yeah, it should be minus length. There we go. Minus length seems to be right. Minus length seems to be right. Okay, I think this one works. I think this one works. Do I still have all the, yeah, we still have all these. Oh, see, a good thing. Okay, ready? Finally. Oh my word. My word, this is terrible. Wow, with prefix sum and pay attention. only collect the sum when I'm gonna collect the sum at index I if Si is a non-prime and Si plus 1 is a prime, indicating that Si can be an end to a previous partition. The runtime improves to ONK. Lordy, is this tough? Damn. As tough as it can get. Wow. Respect. This one's a nightmare. For sure. Seems so innocent, right? Ooh, wee. Tough problem. Nah, I just use this. This is good. Yeah, I got inspiration from here. Yeah, I was trying this one. Didn't work. Okay. Okay. Boy. Boy, those are tough. Tough questions. All right. You guys are done. Convert the temperature. Kelvin or Fahrenheit? Well, Kelvin just Oh man. All right. I mean, we have to stick to the tradition, right? We have to stick to the tradition. Hey, this is an important question. We have to convert to Kelvin. Kelvin, haven't used a Kelvin for ages. I remember. What do I remember? What's that class? Physical, chemistry, physics chemistry, physical chemistry. Man, that class is hard. I still remember this one thing called the formula of Nernst formula, and it deal with entropy, and there are a lot of calculations and stuff. Man, boy, I do not like that. Wait, we can just copy and paste. Oh, it has to be a. It's fine. So it has to be a list. Well, I didn't really read the question, so I have to make sure it is what it's trying to say. Yep, I think it's good. Okay, what's next? Subarrays. Well, LCM, least common multiple. Number of subarrays with subarrays. Okay, with LCM, least common multiple equal to k. How do you find least common multiple? We find the GCP, greatest common GCD. We find a GCD, multiply them and divide by GCD. Okay. So given integer array nums with integer k, return the number of subarrays where the least common multiple of the subarray is the element is k. Interesting. Good question. Simple, straightforward. Let's see. Given 36271, right? We want to find a subarray who, like, every element can be divided by 6. Basically, yeah, that's what it's asking for. So I have to say, like, subarray ending at this. 3 is not divisible. Wait, hold on. Why 6 is good, but 3 is not good? Should be divisible by 6. 3 is smaller than 6, so it's not good. Okay. So ending in 3, right? Then we say ending in 6. How do we find an ending in 6? So we need to find everything is ending in 3. We have nothing. Ending in 6. 6 by itself is good, right? Then but 3 and 6 works. Oh, because they're the least common multiplier. But still, oh, 3 is 3. Single element is single element. Yeah, I was completely wrong. It's okay. It's okay. It's okay. So yeah, okay. So if it's divisible, right? We just say if it's divisible. So if this one is divisible, ending here, how many subarrays have all the values divisible by that? 6 is 6 by itself, and we'll go here. 3 is divisible to 1, so that's why 6 should be 2. Right, 2 by itself we cannot do, so we look in 6. Right, so here, total divisible is 2, which means we can always add the 2, so we have a 2. Right, and then there's no and then. This is no, this is no. So add together is going to be 4. So each one, we're looking for the previous, how many, and then I can always tag along, right? Because it has to end at this. We have to end at this. But yeah, but how do we solve this problem? So for this is a 6. So the first one we find, because 3 is no good. So no. And now we find the first one, then we have to just go forward. Right, we have to go forward. to find if this is good, this is good, this is good, and we find all of them, then we conclude there are two, right? Yeah, so there's going to be a stretch. Right? There's going to be a stretch. You know, why don't I divisible, right? So we just go down. If divisible, we mark it, right? It's the first divisible. Divisible. If it's not divisible, then we just start over, right? Divisible, divisible, divisible. We need to find something that has to be at least k, right? It can be divided by k. When k can divide that, k can divide that. But it's divisible, but it's not, because it has to be, yeah, the single has to be the common, but 3 and 2 also works, right? 3 and 2 also works. But let's say if it's a 12, then we have a 2 and 3. Then that doesn't work, even though they all divide, but that's not. That's not. So what I can do is I find this, I find next, and I need to find their common, least common. At least has to be divisible. So we find divisible, 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 divisible. So if a bunch of them all divisible, right? Then what? How do we find? Yeah, it could be like 2, 3, 2, 3, 2, 3, 2, 3. And then we have a 6. Yeah, once it stops, then we just have to restart. So that's that. That's not hard. The thing is, once we have a stretch of numbers, all divisible by 6, all divisible by k, right? They're all divisible by k. They're all smaller or equal to k. And how do I determine that this stretch, so like here, the stretch is 362, right? 362. Then we just need to find out within the stretch, how many can we form? Man, this is actually more complicated than I thought. Yeah, first thing, they have to all be divisible. So we have a stretch of value. They're all divisible by the k. Okay? They're all divisible by the k. But how do I tell that? If we have 2, 3, 2, 3, 2, 3, and we say k is 12. They're all divisible by 12. So we group them together, but the answer should be 0, right? Man, my form just dropped. The answer shall be 0. Yes, the answer shall be 0. How do we know that? the LCM of this. Yeah, how do I determine it's the LCM? I mean, two values is easy to do. We can GCD them, and then we can find 3. And keep expanding, keep expanding, keep expanding. Until we find a one that makes the current thing with LCM is K. Okay? And if the LCM is K, if all of them LCM is K, then the remaining, they all work. Then we shall start, kick one out, start from here. Right? If we kick one out, we say a bunch of them, the LCM is a certain value, right? And it has to add this in order to work. Which means if we have repeats, then it doesn't work, right? So we go. I think it's a sliding window. We expand the window until we hit LCM. What if we hit the entire stretch and there's no LCM? And that's it. We just keep moving on. But after we finish the entire stretch, boom, we say, okay, this is LCM is K. Then I remove one. Right, we remove a certain value. Then I need to modify its LCM. Holy crap, how do I modify the LCM? Seriously, how do I modify the LCM? I have a bunch of value. I know it's LCM, right? But I don't know, like along this way. But everyone is crucial. That's not true. That's not true. I mean, we can maybe find the factors. Each value we have a factor. Yeah, we can find, the factor that's contributed, right? But what? I don't know what factor has contributed. Huh. How do I do this? I have a stretch of value. Let's say I know it's gonna be k. Okay. Now, I mean everything is done. Now I want to ditch the front. The front will have a value, right? But when I ditch the front, what is the least common multiplier of the remaining numbers? I mean, this is divided by this, right? So if we have remaining value, we have the factor of what this has, then it doesn't matter. Which means, I mean, it's only 1000, so maybe we do need to break down everything into its factor. Yeah, I think I need to break down each thing into its factor. We get a list of prime numbers. Right? We can get the largest value. Right? It's 1000, so we get all the prime numbers, 2, 3, 5, whatnot, and every value we can just go through and see what prime factor it has, right? So we have the prime factor of every value, and the next one we just we add a prime factor, right? We add a prime factor. The largest we add a prime factor if it's in this. Okay, so we keep adding. Right, we have this, and yeah, we do the divisible, right? If it's divisible, we find its current, the prime factor, now the LCM. And the next one, if it's divisible, we find it. If it's not divisible, so we have, now this is what we have, right? This is what we have, and we have everyone's prime factor, right? We have everyone's prime factor. Now we go into this, right? We go into that. Well, then we can actually compute, right? As we go along, we can compute its prime, its LCM as we go along, and we find out, oh, its LCM is, no, it doesn't reach k, right? I say it does not reach k, then we give up. But if we say as we go along and the LCM is k, right, as we go through everything, the LCM is k, so we can try to find out nah, that's okay. We will do the LCM by itself. So everything, we get it, we keep going until we find out the first time LCM is k, then this and the remaining, yeah, they all work. Then we remove the first. We know what factor it is, right? Right, we know what factor it is. And we have a counter. We have a counter of all the factors, okay? We have a counter of all the factors. Right. We have a counter of all the factor. And then we remove first, we remove those factors. And if they're still remaining, then this is good. And if it's, okay, so this is how I'm gonna do it. Oh my god, this is actually not easy. Unless there is a smarter way that eludes me. If there is, most likely there is. But this is how I'm gonna solve it. A combination of, observation. Right, what can I say? Prime smaller or equal to 1000. Should be a prime list. Dude, that's a lot. That's more than I had expected. 168. All right, this is what I'm gonna do. Primes. Man, This is stupid, but it's necessary. You don't want to, like, I don't want to search for the primes. Most of these will not be used, pretty sure. But they say 1000, we'll get 1000. Okay, it's not a lot. It's 100 something. It's okay. All right, so what we're gonna do is we will go through everything, and we're gonna record the start position and we record the end position, right? Okay, so we say for I n in enumerate nums. Okay, if n is smaller or equal to k and k n is equal to 0, we actually have, you know what? Let's have a temp, right? Now we don't need to do this. We just say for n in nums. But we can save space. Okay. And then we say low and high. Okay. So low and high equals -1 and -1. If say low is smaller than 0, then low will equal to I. Okay. Else high will equal to I. Okay. So if it's this, else. Okay, this is something's broken, right? Then if low and high are both actually low equals high equals, right? And then keep going. The next one is good, but low is already not. Then we just update high. Go to the next one, update high, update high. Then we come out, right? We come out. We say if low is larger than 0 and high is larger or equal to 0, that means we have a stretch that we need to analyze. So now we analyze, right? So we analyze. And then after we finish analyzing, we're going to return low and high to -1. We're just done. Actually, we will always return low and high when it's done. Okay, so now we need to analyze. Okay, from low to high, how do we analyze? So for each one, we need to have a counter. Okay, so we say PC equals a counter, prime counter. Then we're gonna go through this one more time. for j in range low to high plus 1, right? So for every one of them, okay, every one of them, we are going to go through the primes and see what factors do I have. Right, for j, so we're just gonna go blah 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 until we find, so I say LCM equals 1, okay? Maybe I need a find prime factors, which means you give me a number, I will return a prime factor. Right, a list of int. Okay, so you gave me an n, right? So we say I equal to 0, while n, if n mod self dot primes I equal to 0, why don't we just return a counter? PC equals counter, right? If this, then we say PC self dot primes I plus equal 1, and then n divided equal to self dot primes I. If this, we keep going, else I plus equals 1. Keep going. Eventually we'll get to a prime and we'll divide it, it'll become 1. So it should be this is larger than 1. Right? Then we'll return PC. So here, PC is this. So for every one, we can find its prime factors. Right? This is the overall prime factor. Then we can say current prime factor equals self dot find prime factors nums j. Right? So we get the prime factors. But how do we quickly do the multiplication? You know what? We can just say PC plus equal to PC plus equal to this. Okay? Then we can find a current LCM. Right, current LCM is just the product of everything. Right. So we find the LCM, so the current LCM. Yeah, so J we go from the start, blah 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 blah, and every time we find the current LCM. by multiply everything, we find the current LCM. Yeah, you know what? I don't like this. Let's say for P in current PC. If P is not in PC, then LCM multiplied equal to P. Right? Once we're done, we say PC plus equal to current PC, and we say if LCM is equal to K, okay, then we can break. All right. Otherwise, we just keep finding. Okay, now when we come out, we can say if J reaches high, right? If J reaches high, no, if breakout, if LCM is not equal to K, then we just don't do anything. There's nothing to do, right? So if we say LCM is equal to K, okay? When we break out if LCM is equal to K, then we have a J. So from the start, from low to J, right? So from low to J, now we can say, we can do, I use I already. Okay, how about I use a Y? Well, let's use X and Y. And now we can say X shall equal to low. Right, now we have X and Y. Then these two we can, you know, making something happen. But I am already doing this. Maybe I guess I can do this. I don't have to do this. So whenever we get a current PC, right? Whenever it's equal to K, what do? I need to know how many, so by itself, right? So the current Y is, and then the current Y, and then everything after it, they're all R, right? So this one is all the way to high, so it'll be high minus Y, right? So I just say high minus Y plus 1. If I have a result, if LCM is equal to K, right? So we do this is equal to K, then from Y all the way towards the end, right? All the way towards the end, they all going to be, and then what? Then I need to move the left forward, or move the left inward, right? So we have the rest, and then we need to move the left inward. We say while true, right? So we're gonna move the left inward until the LCM drops below again. How do we do that? So we need to remove nums x. Okay, remove nums x. Oh shoot, you're gonna find it again? That's bonkers, man. I don't like it. I don't like it at all. We're using this multiple times. Find prime factors. Man, I don't like it. I don't like it. Okay. If this and this, then we say temp dot append. Okay, if not, at least we have a value. We have a temp. Then we're just gonna go through a temp. We're gonna set low and high, 0 and 0. Right? And then we're gonna go through this. Let's say for high, in range, len temp. Right? We're gonna say PC. Say for P in temp high. Right? If P not in PC, LCM multiply equal to P. Okay, LCM equals 1. PC plus equal to temp high, right? So if LCM is equal to K, then here starts our journey. Right, we find it first, then if this is dude, then we say while. Right, so we have this is good, right? Then we add this, and then we move the front in. If it's still good, then we start from here, right? Because this is the first time that everything's good. So we can say while LCM is equal to K. While LCM is equal to K, say rest plus equal to len temp minus 1 minus high plus 1, right? And then we're gonna remove the front, remove the low, right? How do we remove the low? So PC would be minus equal to temp low. Okay. Actually, I'm not even sure if it's possible to do it this way. Pretty sure it's possible. better to check. Yep, it's possible. So PC, that's the overall PC, minus that, right? Then what we need to do is to check that value. Not the value, but we just check to see if anything is becomes 0, then we have to right? So we just say for p in temp low, if PCP is equal to 0, LCM divided equal to P, right? Blah 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 comes out, then low plus equal 1, then boom, we'll go back up, right? And we go back up, LCM equal to K is not equal to, so we have to explore more. Okay, so what if the low chases up to high? I don't know if it chases too high. Well, if low chases up to high, so low plus 1 become high, okay? So what if the LCM is still the same? So they both point to the same thing, and LCM is that thing. Then we will add that, right? Whatever it is, we'll add it. And then we're gonna minus this, okay? And then P in this LCM divided, then LCM will be gone, right? And the low plus equal low will move on to the next one, right? So the low catches up to high, and then when it come out, low will be in front, but high will go on to the next one, and LCM will be 1. And then we're building up it again. Yeah, I think it might work. Right, once we exhaust the high, then we need to reset. Then we'll go back up. Then I'm going to return. Man, you know what I feel like? I feel like I am doing it wrong. I just had a feeling this is not the way it's supposed to be. I'm doing it so wrong. But I don't know what's the right way to do. It seems to be so easy, right? But I don't know. Oopsie doozy. I forgot a K. It is accurate for this. Random? Perfect. We need 2 things. One to 1,000, right? For this in range, let's do do 100. Print test. Print randint. 1 to 1000. Man, this might not be what I thought it would be. But all right. Well, we have a couple more. We can test this. That's a good test case. We can test something like this. Yeah, we can test these two. Let's start with. Ooh. I got an issue. Okay, so hold on to this. Hmm. 5 and 5. That's interesting. K is 5, N is... Oh, shoot. There we go. I don't want to put this at the end. If you know what I mean. Okay, now we can do this massive thing. I bet, oh my god. Uh-oh. I'm all 0. Oh, there are a couple of 1s. Okay, so this is not good. Man, this is not what I expect. I should still do 100, but let's make this smaller. Okay. 10, that should be reasonable. Oh, third from the last. 1, 2, 3. Interesting. I have 18. That is very weird. Okay, that's 18. Right, 1, 2, 3, 4, 5, 6. That's 18. Oh. Oh, shoot. Oh, man. LCM. Shoot. Shoot. It should be everything multiplied together, right? Yeah. You're already doing the counter. I don't know why you didn't do that. It should be, yeah, it should be straightforward. Oh, God. It's okay. But it's depending on the current largest value. If I have 2 and I have another 2, right? We have overall. And so when you divide, you have to take all of them away. Okay, that makes sense. When you multiply, we get a new one, right? With a new one, yeah, you can just multiply everything, but you take a look at the new value, right? And you simply say, is anything new? You multiply, yes. And man, how do we compute? Yeah, how do we like just compute LCM as we add more value to it? Let me think again. We have these factors. It's not just a single factor. It's going to also have something to do with. I mean, every time we have a new, we definitely include it. And a new one. How do we know? You should at least have this many of this and this many of this, right? So what you're saying is our LCM need to I don't know how to consistently in like compute new LCM as a new value rolled in. I don't know how. Yeah, it cannot be the. Oh man. I mean, I can go back to the GCD idea, but I don't know how to remove. Basically, I say I have a bunch of values, right? And I have its LCM. Now, I want to remove one value from it. You don't know, right? Maybe the LCM can be computed. Maybe the LCM as add, we can compute it that way. But when we remove, I mean, that's the current LCM. and I have the remaining. I know how many factors I have, right? So I'm removing, so after remove, I have, let's say, how many factors, how many, and then when you remove this, but what if we have another this inside? I don't know. Yeah. Common factors. The product. Man, we're doing it a stupid way then. So what you're saying is, because it's the product, it's the product of everything, right? Divided by their common factor, the GCD of everybody. Which means I can find GCD of everybody. How do you find GCD of everyone? I mean, if I know the GCD, I don't. What if I want to remove a value? Let's say we have the product of everything, right? Say I know the GCD of the whole thing. You have to keep multiplying then. You have to keep multiplying. So we have A, B, C, D, right? So at the end, what we have, okay, I have A times B times C times D. And then we have the GCD of A, B, C, D. And it's the divide, right? That's that. Now I want to find BCD divided by GCD BCD while knowing ABCD and GCD ABCD. How do I approach that? I mean, I know BCD, that I can compute, so I just need to know GCD, which means if I know the GCD of an array of values and I remove one, what's the GCD now? That's actually a good question. Greatest common divisor. And then I will remove a value. Greatest common divisor. Okay. Which means they all have this factor. Then if I remove a value, if that value greatest common divisor. It's something that they all have, right? It's something that they all have. So if I remove it, are you saying it doesn't change? It'll become more. Oh, it's the products of the prime factors common to all the numbers, but it can also be calculated by repeated taking GCDs of pairs. Okay, so result equal to result, and then the next one. We just didn't talk about, what about removal? Hold on, what we know is GCD ABCD shall equal to GCD, say A, right? This value we know, this value we know, we want to know this value. So is given A and a value, we know it's GCD. Now that could be a lot of different values for this. I feel like that's not the way to go, man. But it feels so, you know. Yeah, you don't know. I'm stuck. I don't know. Maybe. This is. I don't know. Is this what you're hinting at? You do have to recalculate every single time. Make it O(n) squared. Well, in that case, I'll bite that bullet then. Basically, as it means is we pick out all the values, right? And then we're just gonna go from the start to the end, find this, right? The stretch that we have. We have is equal to k, then we compute, and then we move forward, and then we compute again. We move forward, then we compute again. Oh man, I don't like this. But I think this one will work. And the good thing is I don't need any of this thing. Do I like it? No. No way. I hate this. I absolutely hate this. All right, so basically we just for j in range below the high, for t in range j to high, and then what is the product? Prod. Can't just say prod equals nums j. Yeah, that's actually also the nums j. This is at the start. Then there's going to be j plus 1, right? So a new value, so prod multiplied equal to nums t, right? And we say LCM shall equal to product divided by mass.gcd. Actually, that's not right. Multiplied by nums t product and nums t. Okay. Then we say if res plus equal to high minus, because we're on that in t, right? Plus 1. Right? And then we are going to break it. Then go back up. Find the next one. I don't like it. I shall start with 1. Start with 1. Oh, I don't even need to do it. I just need a product. And then will be the product times, that is nums t. And product is going to be 1. So that's going to be 1. times t, right? I'll do this at the end. Okay, so none of all these things. What? It does not work. Oh, I know why. Because after this, there we go. But it is one of the worst I've done. Wow. 2 days in a row. 2 hours. Yeah, I do think this one will work. I think it passed all the test cases here. Alright, I'm gonna try this. I think the problem is I try to... Yeah, I have a problem with this one. I try to find a sliding window solution so that I can solve it in ON, but while I can compute new LCM as the sliding window grows to the right, I cannot figure out a way to find new LCM in O1 time when the left is removed of the window. Eventually, this solution is ON squared, which is, I thought about it. I knew it worked. I knew it would work. But got hang on the possible potential of ON solution. Yeah. You can do better. Wait. There's an LCM? Okay. I did not know. I did not know. Oh, now I see what this problem is asking for. Ah, jeez. I bet the GCDs also can use multiple numbers, right? Oh, God. God. Python has LCM function. Yeah, I mean, in this case, I think it's just... I mean... Hold on. What's current? Current is 1. Current is... Oh, I did not know that. Look at this. Oh, wow, this is correct. Current value, an LCM with a new value will get a new LCM. Wow. Okay. So we say LCM is 1, right? We say LCM equals math.lcm, LCM and nums j. If LCM is equal to k plus equal to... Well, let's get an n. Right, so it will be n minus 1 minus j. And then we shall return the rest. That is not correct. 14. Oh, hold on. It's not towards the end. Oh, no. And if nums j mod nums j is larger than k, or nums j mod k, then we're gonna break. Almost. K mod nums j. There we go. All right, he has another solution. Count the. Let's this one first. Yeah, this is an easy problem. It is slower than this because this one I pick out them first, so it will be slightly faster. This one I did not pick out. I have to. I mean, it's the same actually. It's okay. What do you not want to see? We count unique LCM values for all subarrays that ends at I. Okay, the number of unique LCM values will not exceed the number of divisor k. That's true. What is this? So for each one, right, we'll get if it's divisible by k. No, by k divisible by n. Then we will find the count of the previous I don't understand. What is this? Yeah, I don't want to bother this anymore. Oh, I need to upvote it. Such an easy problem. I don't know. It just took so long. Alright, I shall end it right now. I'll see you guys tomorrow. Adios.